Hello, hello, hello. This is Mr. Crawford. I wanted to take time to talk about this displacement and velocity quiz and give the concepts as an alternative way for you to understand what to do with these problems. It's not about putting an answer, it's not about just using Chat GPT. It's about getting a feel of how these problems work in order to solve them. Because once you solve one problem, you solve them all. And I'm going to change this to like, I wish the green were darker, but I'm going to change it to my favorite color. Let it be green. Okay, as you see on this problem, it said on both paths. Point one is the same, has the same horizontal distance as point two, or it's the same horizontal distance from point two. With that being said, I'm literally saying that the distance is pretty much constant. It makes a straight horizontal line. Then you got the runners start and end at the same time on their respective paths. So what's going on is if I were to make this into a graph, this is where both the seconds and the meters are zero. This would be the meters, and this would be the seconds. Or the distance. I'm calling it meters, but I could just literally call it distance. All right. And the starters, the runners, they start and end at the same time on their respective paths. So as you see, we want to be able to talk about the average speed and velocity. So let's select all that apply. With runner number two, and I'm going to take all of this out. I'm going to erase everything. Oh, I could press Alt Z. With this, you can clearly see that from this right here, if we're assuming a meters versus second type of graph, that runner on path A has a smoother run than the runner on path B. And with that smoother run, you have a higher velocity because the rate of speed is not it's not changing. It's not being positive or negative as you see with runner number two. I mean runner number B. So what's going to happen is since runner B has more distance, since that person's distance is greater, it's going to have greater speed. And we're assuming that they end at the same time. Without that assumption, this will be way more complicated. Now, with that, we know runner A has a greater velocity because we don't really see much of a change when it comes to the the, the velocity. We don't see much of a change when it comes to the displacement. As you see, the displacement is fairly consistent, where most of it has a negative slope, and then you have a slight positive slope. Whereas with runner two, you have this big positive slope, and then this even bigger negative slope, and it kind of cancel each other out. Or better yet, you could just say the smoother curve allows for a greater displacement. And that's what we have here. Alright, young people, I decided to change the color to red because it's darker. As I was doing this, I realized it's not that easy to see. Looking at this, we have a table. If you look at the units, we have meters per second, or a type of distance versus a type of time. And with that being said, whenever we have a table, if you're good at looking at the numbers and visualizing, you are going to be in a great place when it comes to doing this type of problem. Because you don't have to make a dot diagram as they say make a dot diagram because of the fact that you can visualize. If you want to make a dot diagram, this is what you could do. And let me see. I should have made sure I had the whole window when I did this. But yes, so I'm going to just explain it verbally. You can go to desmos.com. On the top left, there's a plus sign. You can click on that plus sign and press table and put in these numbers. But if you are a visualizer like me, this is what you could do. The term goes up by increments of 1 second. In the first 4 seconds, the meters go up by increments of 2 meters. Notice how I keep up with my units. You want to be as detailed as possible. So from the 4th to 5th second, the distance went up by 1 meter. And also, I do want to point out, and this was me kind of using my ebonics, but if the number is less than 14, spell it out by 1 meter. Then, from the 5th to 6th second, the distance stayed the same. So notice, when I first started, I talked about the first 4 seconds going up by 2. For the 5th to 6th, we had no change. And for the remaining time period, the distance changed by 1 meter, 3 meters, 5 meters, and 7 meters. So in terms of velocity, because they want us to talk about in terms of velocity, the speed was 2 meters per second. Then the speed went to 1 meter per second. Then to no speed. Actually, in terms of velocity, that don't make sense that I go from velocity to talk about speed. So I'm going to change the speed words to velocity. Velocity. Besides write 0 meters per second, I put no velocity. And finally, though the path is linear, it did not increase consistently in order. I would say proportionally. Yes. Because to increase consistently, yeah, in order to increase consistently, it has to be the same increase in order to gain a good speed. To easily determine the speed. Yeah. To determine the velocity. And in this case, there is a velocity and there is a starting distance where the equation will follow y equals mx plus b rather than the easily y equals mx. And that's about it. And if this is hard to see, hopefully you... Let me try to zoom this in. Yes. I'm going to zoom this in a bit because it's easy for me to talk about it. I will advise you guys to pause at this part of the video around 12:55. And there you go. All right, we're on number 3. We have a meters versus time graph. Whenever we see a horizontal line, automatically constant velocity. I mean, not constant velocity, no velocity. Because there's no change in the position. When we see a line that is sloping upwards, constant velocity in the positive, constant velocity in the negative, and this curve right here makes the velocity non-linear or non-constant. And that's all you needed for number 3. These problems are made to distract you. You have all this information here, and honestly, wherever you have a word problem, is you got to pick your battle whether you're going to read it or not. And it will take time for you to determine when to not read a problem. Like, for instance, with those physics problems, when they ask about the braking and then there's a change of speed, you will have to read them because they give you written hints without numbers. Luckily, with this problem, you honestly don't have to read it because of a couple of concepts that are hidden. But I'm going to read it anyways, just for teaching sake. Airplanes are considered the quickest form of travel to domestic and international cities. Traveling at about 300 meters per second, an airplane can travel longer distance at higher speeds than other common modes of transportation. However, the distance a plane can fly is often dictated by the location of landing strips at airports. The high traffic skies come to create major airports in some of the United States' most populated cities. These airports can carry millions of people to domestic cities as well as international locations. Some major U.S. airports are shown on the map. Now, with this, notice how the problem gave us the speed of airplane travel. They gave us the velocity of airplane travel. And in this case, velocity and speed are the same due to the fact that they're both positive. Now, notice what the question asks. And this is how you can tell that you did not need to read the problem. Hold on, let me erase these old markings. Notice the unit. In the problem, they gave us meters per second. But here, they gave us kilometers. So in order to take care of this type of problem, I am going to use an off-screen calculator. But I'm going to write the work here. I'm going to use the Pythagorean theorem. And just to give you guys a hint, perpendicular directions. East, north, west, south. East, south, and west, north. This is something you guys are expected to know in everyday life. If you watch this video and don't know this, you're setting yourself up. And not in a good way. You're setting yourself up because eventually these tests, these exams will get tougher. It is best to take the time to know this so you can do whatever you need to do to succeed. And the beautiful thing about using the Pythagorean theorem when both directions are perpendicular to each other is all you gotta do is square and add and put a square root over it. And I'm going to give you that imagery very soon. So I put my extra long square root. Pick the 1454.55 plus 390.27. And after I put that in my decimals calculator, I get 1505.9, or actually 0.89. But what's going to happen is this is going to go up to 1506. And I will pause to answer the phone. So after I do my rounding, I get 1,506 kilometers. And if you notice, going to Charlotte matches with 1,506 kilometers. So we just mark it and move on. Oh, wow, this ain't listening to me. Wow, that was interesting. If you notice real quickly, this problem is the exact same thing says the exact same thing as the last problem. So we're still using the same prompt. But let's look into the instructions. There you go. So we have a plane that flies out of Atlanta to Tampa, then continues to Detroit from Atlanta. Now they're asking, how does the airplane detour impact the plane's total flying distance to Detroit? That's all you have to put. Something that simple. I have to send this text. Okay. Now they want us to include the final distance and a resultant displacement amount. So what we have right here, if you notice the east to south and the north to west, those distances are perpendicular as I mentioned on the last problem. Hold on. Yes, they're perpendicular. With that, they could be looked at as vectors. So what I want to do is let's find the final distance. So to find the final distance, I'm going to do the Pythagorean theorem with the 211 and 618. And one thing I like about using this Desmos calculator, which you guys cannot see, is that I can copy and paste my behind off and make life a little bit easier. There you go. So what I'm going to do is I'm going to rewrite the Pythagorean theorem in a different form. So I have 211. I guess I have to press this button again. Plus 618. And then I'm going to square it. Now I'm going to raise it to the 0.5 power. You know what? I'm going to try this. Ooh. I'm not trying that. There you go. So from Atlanta to Tampa, I'm just taking these two numbers and I'm just adding them. And that's going to give me 653.03. And then from Tampa to Detroit, oops, DT dub. I'm going to give you 1580. And press a little button. So I gotta press the space button. So as you see, I'm trying to get used to this software like everybody else. You know what? I'm gonna leave this alone. Oh, that's work. That works. You know what? I'm gonna make this 1582 because they said 0.99, and I'm not gonna put myself through that extra stress. There you go. So right here, I have the distances for each distance. So from to ATL to TPA to DTW, we're going to have 1582 plus 653.03. And why am I putting these parentheses I don't need to put? And this is going to give me 2035.03 kilometers. Now I want to find the resultant. To find the resultant, so this is what I'm going to do. I'm going to take the 211 going east. Then I'm going to subtract 79.5 from that 211 going east. Then I'm going to square it. Because I'm looking for the horizontal directions. And then I'm going to look at the vertical directions. The north is the 1580 minus the 618. And this is how I use the Pythagorean theorem when I type it. And I'm just typing it in here. Based on significant figures, I will make this 971 kilometers. There you go. And that's it. That's how you find the total distance, where you're breaking up each distances and using the Pythagorean theorem twice. And you find the resultant, where you look at where you're projecting as if you are going straight from Atlanta to Detroit, which is up here. You know what? I got this magic pen. Let me make this money count. So, with the resultant, we are picturing as if we're going straight here with the resultant to Detroit. I've been to Detroit, so that's easy for me to mark. And with the total distance, we are going from Tampa to going from Atlanta to Tampa. Then we're going from Tampa all the way to Detroit. That's what we're doing. And that's just an approximation because I didn't zoom in correctly. There we go. So that was a process. But again, allow yourself to get comfortable with these processes and they will get easier. Anybody tells you that this will stay being tough or this will stay being a nuisance, that person is not telling you the truth. Allow yourself practice and it gets better. All right, young people, let's go ahead and look at what's going on here. Right here, point A. Oops. I might want to turn on the pen. So, right here, point A is at 1, 5. Point B is at 2, -1. So, when I do this, I'm going to take the ones on the left side of the coordinate, 1 plus 2. I'm going to get 3. Then I have 5 minus 1. I'm going to get 4. And again, when we are adding and subtracting vectors, especially when they're not on the same line, when they're not 0 or 180 degrees from each other, when they're 90 degrees perpendicular to each other, we're using the Pythagorean theorem. I expect you to know that with a Pythagorean triple, that when our perpendiculars are a length of 3 and a length of 4, you should automatically know 5. You should not waste your time doing any math to solve this problem. That's a Pythagorean theorem, and I'm going to get that posted enlarged so you can see it. Okay, let's talk about this. And this one, I'm going to do it by typing. All right. Student A claims the dog accelerated away from the owner after 4 seconds, turned around, and back to the owner where the dog started. Student B claims that the dog accelerated away from the owner but did not turn around and run back to the owner where the dog started. So with this, we have a velocity versus time graph. I guess I would do some marking with the pen. We do have a velocity versus time graph. With that, notice the focus is on position. Okay? So this means position is equal to area velocity versus time. The operation that we're using is multiplication. We don't have to do any math because we have eyes. Math is based on our observation. So student B is correct because after finding the area of the curve, you will have a positive area, not a 0 area to show that the dog returned to the owner. And you know what? Symmetric, let me teach you something new about the x-axis. There you go. Now, that's one reason. We need a second reason. Student A claims the dog accelerated away from the owner, and this positive acceleration can work. But notice, it had to accelerate for 4 seconds. So technically, it did accelerate away from the owner. But for me, student A, yeah, it did accelerate away from the owner. And then what happened is the acceleration went slower. So this slope of the line is positive, and then it becomes constant, and then it becomes positive again. And what happened is the acceleration, the dog was slowing down to a constant speed. That does not, with the acceleration being zero, that does not mean that the dog went back. It could have meant that the dog either started running at the same speed, found a comfortable speed to keep running, or the dog stopped running. But it does not mean that it returned back to the owner. And we needed the slope. That's it. So, based on what you saw on the graph, you were able to easily see the division. But when it comes to position, you needed the area. And that's it for that problem. Right here, we want the velocity. We have meters versus time. That means we're finding the slope. 1 through 6. So at time is 1. So with the 1 we have the 0. With the 6 we have the -4. And now with the 1 to 4. So I'm going to do 1 minus 4, and with 4 we had 0. So this is 0. Okay. And that makes sense. Now, with this one, 3 to 5. 3 minus 5 with 3. We have the 5. With the 5, we have the -2. So I have 7 over 2. -7 over 2. Then we have the 2 to the 4. With 4 we got the 0. With 2 we got 2. So this is -half. Then I got one more. 5 to 6. -2. 6. This is going to be regular 2. And this is going to be -1. Now, while ordering the velocities, we include magnitude, not direction. And we want to order from least velocity to greatest. So our least velocity, in this case, is going to be the one with 0. 1 to 4. And we're going to look for proper fractions. I'm ignoring the negative, so 2 to 4 is next. Then another proper fraction where the numerator is smaller than the denominator. This is going to come third. That we have 5 to 6, which is 2, and 7.5 is 3.5. That's it. Okay. Now, young people, we have a track. And honestly, I'm not going to put too much energy into this one. You guys understood that student A was farther from the center, so they had more distance to run. We assumed that they finished at the same time. So their velocity was the same because they finished at the same time and the same place. But the speed of student A was greater due to the fact that they had more to run. I'm not even going to type this. You guys nailed this problem. And it was, for me, when I gave this problem, I was like, I was a little scared. But you guys took my fear away. And I'm very proud of you guys. Now, we went from Beijing to Shanghai. And then we went back. They're symmetric, but they're not symmetric about the x-axis. So this is already wrong. This, we have symmetry. We want to go somewhere and go back. That works. Now, this works when we have velocity versus time and we want the area. Now we have meters versus time. So notice the meters change. We drove however we drove. Then we stopped for a little bit and then we drove back. So that's why C is the correct answer. And let's look at E. Velocity versus time. I'm thinking E could also be an answer. But that slope. E also could be an answer, but when I look at this little distance right here, and I look at this little distance right here, I'm going to say no. Their slopes aren't the same. It kind of got me for a little bit, but their slopes aren't the same. So there you go. And there's no symmetry right here. That's it. I'm done talking about all 10 problems. This is my first video, and that's about it.